Product layouts are most closely associated with assembly lines, so you wouldn't normally think of a restaurant being a product layout, but the fast food drive-through is essentially an example of a product layout in restaurant service, and you can see that in this particular problem. Considering the following diagram of a fast food restaurant drive-through with 3 stages for each car to follow the path described by the arrows in the diagram below. See, there's this one unchanging pattern of production. The time required to complete the work at each of these workstations is also listed here. All right, so I see that each car stops at the menu board and the business there takes about 2 minutes, then proceeds to the first window where they process the payment, and that takes about 1 minute, and then the second window, that takes about 3 minutes where they actually get the meal, and then they're gone. Now, here's the key. This is, in fact, actually a product layout, which means that all the concepts and relationships of cycle time relate to this fast food drive-through. That's what the questions are asking about. All right, now speaking of the questions, what's the first one? What is the maximum rate at which the restaurant can successfully serve arriving cars at this product layout? Maximum rate. Now, remember, this is a product layout. Okay, that means it has a cycle time. If it is working at its maximum rate, it is working at its minimum cycle time. The shorter the cycle time, the faster the system's running. So the minimum cycle time is the fastest the system could be running. That's the key here. What is the minimum cycle time? That's the fastest that you can run this particular system in the diagram. Well, the minimum cycle time will be the largest of the tasks along the product layout. Oh, which means, okay, takes 2 minutes here, takes 1 minute here, takes 3 minutes here. Think of these. I know that some of them are more than one task, but they've been bundled together. Think of them as essentially then tasks. The cycle time cannot be any shorter than the largest one, because if it is, then there wouldn't be enough time to do that. And I keep pointing at this one that it is 3 minutes. Yes, minimum cycle time at this drive-through is 3 minutes. Why? Because if we try to push cars through there any faster, they're not going to be able to finish their business at the second window. All right, now that is a form of an answer to this question, but it's actually not very, very helpful. Okay, because we're just commenting on the budget of time at each window. The question asks, what's the maximum rate at which this drive-through could be operating? Okay. Now, given that it has a cycle time of 3 minutes, that means that one car leaves every 3 minutes. We are successfully serving a car every 3 minutes. So, in order to comment on, now you could say that. One car served every 3 minutes. I mean, that would be an answer to it. Rates, though, generally the manager wants to know the number of cars over a time period. Let's see, every 3 minutes, 60 divided by 3 means, and this is a more common way to state a rate, that's 20 an hour. Okay. That's basically a more appropriate response. Any of the things that we've listed are true statements, but at maximum this particular drive-through can serve 20 cars an hour, generally on average. No, all right. What's the next question? An average of 15 cars arrive each hour at the restaurant's drive-through. What does this imply about the efficiency of this layout? Now, this is actually a sneaky question, because it asks about the efficiency of the layout. You say, oh, all right, well, we've got this fact about the 15 cars arriving, except wait a minute, it's a product layout. So if you're just commenting on the efficiency of the layout itself, well, we know that that is the sum of the task times total amount of time that's essentially invested in each car in this particular problem, divided by the cycle time times the number of workstations. That's the formula for the efficiency of a product layout. Oh, okay, well, we can fill that out because, let's see, the sum of the test times, that's the total amount of time that's invested in each customer's car. So that's the 2 minutes plus the 1 minute plus the 3 minutes, essentially 6 minutes worth of work for each car. So that's in the numerator, 6 minutes, divided by the cycle time, right? We're assuming that they are operating at their most speediest. So 3 minutes times, there's 3 workstations, essentially. 1, 2, 3. So 6 divided by 9.6667, or basically, what would that be? About 67%? That answers the question, okay, like about 67% efficient. That answers the question of the efficiency of the layout. Now, what's tricky about this is we say, well, wait a minute, we didn't use the 15. Yeah, we didn't use the 15 to comment on the efficiency of the layout. For kind of like an advanced analysis, you could deduct what's the total, essentially, efficiency of our use of the employee's time at that arrival rate of 15 cars. But that's a different question. And if you're kind of curious about how you would do that, the best way to do that is to think in terms of an hour. Okay, there's 15 cars arriving in an hour, and each one of them is 6 minutes worth of work. And what we're assuming is we have 3 employees, 1 for each workstation, and an hour. And this is how you would tweeze out, and you could check me on it. Well, if all those assumptions are true, actually our efficiency of the use of the employee's time is only about 50%. But that's not what was asked, just the efficiency of the layout. That's also assuming the employees don't do anything else while there's not a car in front of their station, and that's generally actually not true in these type of facilities. There's a lot of multitasking going on. Anyway, the formal efficiency of the layout, 67%. We just fill out the formula. Last question. The employee who works at the first window where the car's payment is processed has just left the restaurant due to a family emergency. To keep operating, the restaurant has closed the first window, and the employee at the second window is now doing the work required at both windows, processing and paying and providing the meal and everything. Now, due to the change, what's the maximum rate at which? Okay, so similar to the first question, except the system has changed. Helps to go back to the diagram. This employee left on a family emergency. That means we closed down this station. And what they have done is taken that work and added it to this station. Oh, this station used to have 3 minutes worth of work. Now it has 4 minutes worth of work because of this change. The question is, what's the maximum rate? All right, what's the minimum cycle time? Now we only have 2 stations. One does 2 minutes worth of work on each car, and one does 4 minutes worth of work on each car. The minimum cycle time now is the larger of the 2. I'm just going to write min CT for minimum cycle time, right? 4 minutes. Okay, that's the cycle time. They are asking for a rate. So if you are serving 1 car every 4 minutes now, 60 divided by 4, we are just revealing, so to speak, that that's what, 15 cars an hour? So, due to this change where they shut down the 1 window, and notice that they added that work to the second window. Too bad they couldn't add that work to the menu board, but that's not what they did. Since they added that work to the second window, where once the drive-thru could serve, what was that, 20 cars an hour? Now it can only serve at maximum 15 cars an hour.